Mark Herbert is the VP of Biopharma Business Development at Varda Space Industries. We talked to him a year ago on one of the most popular episodes of this podcast I've ever done, and he's back to give us a little update. So, Mark, welcome back.
Good morning, Chris. It's great to be back.
So, Varda, we talked last time about manufacturing drugs in space. A couple months ago now, I think it was, you brought back a capsule of your space manufacturing lab back from orbit. So tell us about that mission, what it was all about.
Yeah, so last June, we were the first company to launch a satellite on a SpaceX Falcon 9 rocket. We were one of 35 satellites on the rideshare constellation that was launched in June of 2023. And we finally brought our spacecraft back home after orbiting the Earth for about 8 months. It took us a little longer than anticipated because we had to work with the FAA on what is called a Part 450 re-entry license because, yes, we are one of 35 satellites contained on that rideshare Falcon 9 trip to low Earth orbit, where we're the only one that had re-entry capabilities. And so we brought our spacecraft back down to the Earth on February 21st, landed in the Utah testing and training range, and successfully received the spacecraft and analyzed all the samples as well. While we're in orbit, we actually reproduced the science that was demonstrated terrestrially. So when we were developing custom hardware for in-flight applications, we discovered a new form of ritonavir, an HIV drug that was initially commercialized in the late 90s by Abbott to treat HIV. Unfortunately, 2 years after commercialization, they had noticed a new crystal form in the commercial supplies, and so it resulted in a massive recall of the drug. So it's one of the most studied drugs in small molecule crystallization. And during the hardware development, we discovered the first new form in 24 years, which is a metastable form. And then we reproduced that production in low Earth orbit using fully autonomous hardware. We also demonstrated that we were able to fly all forms of ritonavir. So the amorphous form, Form 1, Form 2, and Form 3, which was the metastable form, fly them in orbit, bring them back safely in a conserved fashion. And so it was great to reproduce the terrestrial science, but also show that in a complete mission that we have complete stability and control of all of our pharmaceutical samples through that conduct.
Wow. Okay. So much there. So first of all, 35 satellites went up on one launch. Is that what you're telling me?
That is correct. Yeah. So this is what SpaceX offers. They offer rideshare, and that's to promote the expansion of the low Earth economy. But we are the one satellite across those 35 that actually had re-entry capabilities.
Right. And the size of your capsule is, I don't know, diameter 6 feet maybe, and height 6 feet, if that.
A little smaller than that. We like to say our capsule is huggable. So it's about 1 meter wide, 1 meter tall. I can put my arms around it. I can't pick it up. It weighs about 300 kilos when it's fully assembled. So it's quite heavy.
Yeah, I'll bet. I'm just kind of stunned. I'm trying to imagine the size of the other satellites that are going up. They're not all that big then. I mean,
They're not. Yeah. So most of those satellites are telecommunication satellites, which would be, a fraction of the size of our spacecraft. But our spacecraft is designed specifically for the conduct of pharmaceutical research in a microgravity environment. Obviously, that's impossible to replicate on Earth. So it has different utility and different function than those other communication satellites.
Right. It's actually doing stuff. I'm amazed at how small electronics can be. I mean, we all carry a computer in our pocket now, so it's not that big a deal.
It's pretty powerful, the engineering feats that are being taken today by the next generation of students. But the one thing that we have to worry about in space is we are limited in space in terms of the size of our spacecraft, but also in terms of energy consumption. So all the hardware, all the processes that we're developing are done in a space limited, energy limited fashion. And so there's a lot of actually utility for the processes we're developing in space for terrestrial applications to conserve energy and reduce footprints in terrestrial processes.
Yeah. So the next thing was, and I don't want to forget them, but re-entry permit and than all those controls. So let's talk about the reentry permit, because I'm thinking you sent this thing up not knowing, right? Like when you're going to be able to bring it back.
Yeah, so when we launched in June of 2023, we were aware that we had to seek a reentry license. The anticipation at launch was we were going to complete that process with the FAA and our landing site in a couple month period time. Unfortunately, it took us about 8 months, but we were successful in completing that process, satisfying all the safety and paperwork requirements for the FAA. And now there is a Part 450 that's in place that allows companies such as Varda or other organizations that are building satellites with reentry capabilities, either to service the pharmaceutical industry or other industries, to actually lean into this regulation to allow for reentry of those spacecrafts. But it wasn't an easy thing.
Yeah, the paperwork I'm sure is not easy. And then there has to be a lot of planning around when and where you're coming down so that.
Yeah, it's a very complicated process to engineer. So when we re-enter, our spacecraft actually re-enters over Greenland, and then it touches down in Utah about 35 minutes later, which means it's coming in quite fast, about Mach 25. And that means we have to clear a lot of commercial airspace to ensure that there isn't any potential for concerns around, our reentry path and other existing, airspace paths that are going across the U.S. And so over about a 35-minute period of time, we actually cleared a lot of the commercial airspace over the western half of the U.S. to ensure that there wasn't any risk associated with our reentry.
Yeah, I find that amazing. Okay, last little bit on this section is one of the things I didn't think of, but certainly makes sense, is that you sent up different forms of ritonavir as a control to see would they come back the same as you sent them, to know, for example, if you made some ritonavir in orbit, which I assume you did, and it didn't come back like you expected, you would know it was reentry or whatever that changed it. But apparently everything comes out okay.
That's exactly it. So we included positive controls to show that during storage at the SpaceX launch, during the actual launch, during the on-orbit processing and the full reentry, that we can conserve the stability of those samples, that there was no concern around that long-term storage or the condition that those samples were exposed to during those processes. We also demonstrated that we actually could take a amorphous form of ritonavir, convert that to form 3 in orbit, which is actually, we'll take that back. We also showed that we can convert a stable form of ritonavir to a metastable form of ritonavir in orbit and bring that metastable form back down to Earth without any changes in the actual composition of that material. Which was the first demonstration that reentry would not impact the actual integrity of those small molecule samples that were processed while in orbit or transported while in orbit.
Right. So the things I'm thinking about, and tell me if there's maybe other considerations. One, it's up there for a long time. As you say, I'm presuming it's pretty cold, but obviously there's electronics or energy used in orbit, but somehow you managed to have enough energy for 8 months to presumably keep the environment inside the capsule consistent. And then there's the temperature possibilities of reentry, although astronauts come back and they're not, totally fried. I'm just blown away by the whole thing. And then the acceleration and deceleration, like even on the softest landing, something's happening, right? So have I covered all the possibilities for things to
You have,
go
yeah.
wrong?
So it's a fairly complicated process with a lot of potential, failure points along the way. But just to remind yourself, our spacecraft doesn't have any power associated with it. So all the power that we get while we're in orbit is from a satellite bus. So we actually have solar panels that are on our satellite bus that actually provides our propulsion as well, that positioned us for the right reentry paradigm. When we launched in June, we weren't anticipating staying in orbit for a period of 8 months. I think most of our
Yeah.
or actually our first mission and all of our future missions will be in orbit for at most a couple months. The actual time in orbit will be tailored to the actual pharmaceutical processes that we were running. But the extended time in orbit was strictly to the actual paperwork process that we were working with the FAA. But throughout that time in orbit, we can maintain excellent thermal control on the spacecraft. We have all that information captured through that 8-month period. And we can show that within the interior of the capsule, we can maintain within 1 degree C a stable temperature throughout that whole on-orbit duration. Throughout the re-entry as well, which, as you indicated, was quite forcing. So we come in at Mach 25. The surface of the spacecraft experiences 3 times the temperature of the sun due to the friction of coming in through the atmosphere. Thankfully, we've been able to in-license some novel thermal protective shields from NASA that protects the interior of the spacecraft from that extreme thermal conditions. And we showed that throughout the whole re-entry conditions, we were able to maintain, again, with a plus or minus 1 degree sensitivity, about 7 degrees C on the interior of the spacecraft. The warmest our spacecraft got to was when it landed in Utah and was just basking in the Utah sun. And it warmed up to about a balmy 21 degrees C while our team was going in there to recover the spacecraft.
Wow. Which is just room temperature. So I'm also now appreciating the challenge of keeping the temperature constant in orbit as it goes behind the Earth, presumably. So twice a day, or several times a day, I presume, going around shadow, sun, and all maintained by solar panels, and you can keep the temperature inside within 1 degree.
Yeah, pretty phenomenal engineering feat. Our engineering team is a lot of former SpaceX engineers. And so, yes, you give them a challenging problem or proposition and they quickly can solve it. And it's pretty amazing in terms of the thermal control that we were able to achieve throughout launch, the in-orbit production, and the reentry.
So I imagine there's a ton of telemetry going on through the entire mission. Is that
That
and
is correct.
constantly watching those things. Also, how long, for the transformation from one form of ritonavir to the other, that experiment, even though you're up there for 8 months, I imagine happened once and maybe took a couple hours, if not a couple minutes. I don't know. What was that?
Yeah, so we actually completed that experiment back in the summer of last year, and it took about a 48-hour period from start to actual completion of the process, and it mimicked the terrestrial process that we actually developed prior to that flight.
Yeah. And then your scientists are sitting there waiting for another 6 months to find out if that worked or not. That is amazing.
Eagerly waiting.
So, yeah, that makes waiting for tissue culture cells to grow, seem like nothing.
Yeah, so one thing I didn't note, though, so while we were waiting for the spacecraft to return, we were actually developing terrestrial processes to position future flights for success. And so a week after we actually returned our first mission, we unveiled our first hypergravity publication. And so we built a hypergravity facility within our El Segundo facility. It's a centrifuge that allows us to look at increased levels of gravity so we can increase gravity from 1G all the way up to 5G. And we develop pharmaceutical processes and understand the gravity dependency terrestrially before we can fly those processes. And we do this to anticipate the results of microgravity. In late February, we released the first publication coming off of our hypergravity platform that showed that we can develop gravity-dependent processes to shift the particle size distribution of a small molecule drug. And so this is the first demonstration, and it had actually never been, appreciated or embraced by NASA in the 50 plus years of microgravity research that's been conducted by orbital space stations. No one has thought about looking at hypergravity as a screening paradigm to down select molecules or down select processes prior to flight. And so Varda's happy to finally unveil our hypergravity platform and the ability to actually look in a medium to high throughput fashion at a wide range of small molecules and processes to show that we actually can build these gravity dependent processes prior to actually taking them to lower orbit to demonstrate the value that microgravity can have in that condition.
Say a little more about that. So you're now increasing the force of gravity as opposed to decreasing it, which we covered in the last episode with you about why making things in a zero gravity environment can affect particle size distribution. But presumably, maybe you don't always want it at that end of the spectrum, and you might want a different distribution through hypergravity, or are there other aspects to making whatever outcome you're looking for?
Yeah, so there's other aspects of it. So you can think of hypergravity almost as a negative data set. And so we can understand and anticipate the impact of increased gravity. Then we should be able to understand and anticipate the impact and the value of, microgravity. There's nothing special about 1G. We just happen to live on the Earth, and 1G is a arbitrary number that's tied to the gravity that we feel. But as we sit in Varda, our whole value proposition to the pharmaceutical researchers is, can we bring in a new knob to the research lab? And that knob is gravity. And if we can understand how increasing or dialing up that knob does in a specific process, then we should understand and be able to anticipate how dialing down that knob would actually generate or create benefits in that setting. And so we're doing that because it's much easier to screen things in a medium high throughput fashion terrestrially. We also have a lot more analytical methods that we can look at, terrestrially as well, to understand, what variable is impacted mostly by gravity. And then we can use that information to design experiments that will have the most impact for flight. Because the same thing that I talked about earlier in terms of the processes, the hardware, we're somewhat constrained by our space within the spacecraft and energy. And so we want to make sure that everything we do fly has the highest probability of success for achieving the result that we anticipate.
Yeah, so you're using the hypergravity essentially to, I'm guessing, draw a curve and extrapolate backwards to say, here's the trend as gravity goes up. We presume it goes the other direction when gravity is decreased. And this is what
That's
we
exactly
expect
it.
to find if we do this in orbit. Got it. So I see that on your website, you are planning for monthly re-entries next year. Do I have that right?
No, not next year. So I think from our perspective, operationally, we are not constrained by our spacecraft. And so if there is a need on the pharma side, we can design spacecraft, design experiments, and support launches on the monthly cadence. Currently, we are set up and we already booked for every ride share on a Falcon 9 between now and the end of 2026, which gets us on a once a quarter cadence. There are additional opportunities for us to increase that cadence again if there is, demand needs. But just from a operational perspective, we're not constrained by the number of spacecraft we can build. It really is just if there is demand, we can satisfy that, and we can support the launch paradigm of one per month and reentry of one per month.
Nice. All right. So what does the future look like? What other kinds of things are you looking to do besides, for example, are there things outside of pharma manufacturing, or that's the primary focus in just looking for different compounds that would benefit from being synthesized in orbit?
Yeah, so primarily we're focused on small molecule crystallization between now and the end of 2025. The mission that we ran last year and just brought back home in February, and the subsequent missions between now and the end of the year, are looking at simple melt cool processes. So taking a small molecule, melting it from the solid state to a liquid state, understanding how a microgravity environment can promote novel crystallization outcomes in that setting. In 2025, we'll be moving to solvent-based applications, which will open up the number of small molecules we can actually test in that setting, because a lot of small molecules have stability issues that are tied to the melt process. We can overcome those stability issues by implicating solvent-based processes. And then in 2026, we will finally launch biologics. which means we can get into the Keytruda example that we spoke about in our last podcast, where a lot of biologics are constrained because of terrestrial agglomeration sedimentation that doesn't allow them to be formulated into subcutaneous, and so they are tied to IV injectables. We feel that a microgravity platform can start to shift that paradigm by overcoming these sedimentation, agglomerization challenges and promoting these subcutaneous routes of administration for biologics. And in 2026, we'll finally be positioned to support those assets.
Wow. That is, of course, all of this is stunning. Just growing up during the space age, but now thinking that in the future, I or my children may receive a drug that was manufactured in orbit is pretty phenomenal.
Pretty spectacular.
Yeah. Is there anything I missed?
The only thing else that we announced in the last quarter was we did complete our Series B financing of $90 million. So we've total raised over $145 million to date, which means we're well capitalized through 2026. We've got great traction with top 20 pharma as well as mid-tier biotech. And so in the coming months, we hope to announce the first couple partnerships coming out of some of those conversations. And so just happy to be, a pioneer in the space, happy that Elon Musk has invented the reusable rocket that makes low Earth orbit finally accessible to Varda and the pharmaceutical industry. And, just amazed to be a part of this paradigm shift, very similar to you. I never expected to see this in my lifetime. And I hope to, allow our platform to overcome a lot of the challenges that, the researchers are experiencing on these next generation drugs. And hopefully we can help usher in some therapeutics that would not be possible because of the 1G environment that we live in today.
Very nice. Mark Herbert, thank you so much for sharing that with us. This has been, a treat as always. It's really exciting. I'm sure my listeners will be fascinated with this one.
Pleasure, Chris. Thank you.